Hi guys, although drive belts were already around in basic form in the time of the ancient Greeks and Romans, they are real high-tech products. Why is this? A drive belt is developed in accordance with specific requirements. Some run in oil, some have to withstand fluctuating temperatures, and others have to transmit special tensile forces. And they must do so over the course of millions of reverse flexing cycles and hundreds of thousands of miles in the engine. And not only efficiently and safely, they also need to run quietly with little vibration. So belts really have their work cut out. To ensure they are capable of all this, every new product is inspected in our R&D test laboratory. Today we'll be looking at how this is done with the help of Tim Fiss. Hi Tim. Hi Stefan. Thanks for finding the time to join us today. We want to take a look at how new products are tested before they are brought out. It's my pleasure, Stefan. We have over 150 different tests at this site, and we can take a look at a few of them together now. Great, let's have a look. Off we go. Here we can see the chemical resistance test for our belts that run in oil. The belt is stored in hot oil containing 25% fuel and acidic additives for several hundred hours, after which it is taken to the test rig, where we carefully check whether it meets the criteria for expected product lifetime. What's the point of the belt running in oil? If the timing belt for the camshaft drive runs in oil, it produces around 30% less friction than a chain. That makes a difference of 1 gram of CO2 for every kilometer. The length stability of a timing belt is also 3 to 6 times greater than of a chain, meaning that the engine's timing is maintained more precisely. And this is where you test all sorts of different fluids found in oil. Fluids that can get into oil, as well as all kinds of different oils. We have created several hundred mixtures of oils with acid, with used oil, with soot and with combustion residue as our chemical media, which are then heated here and have the belts placed into them. Afterwards, we test whether the belt is still 100% resistant and has not suffered any adverse effects. This here is our ozone test chamber, where all compounds are tested for ozone resistance. What's the problem with ozone? Ozone is a natural gas that is present everywhere in the air. It is reactive and attacks organic substances such as rubber. Ozone causes cracking on the surface, and it's essential that this is prevented. So here we check all compounds for our timing belts and multi-V belts to ensure they are completely ozone resistant. So it's impossible to prevent ozone coming into contact with the belts? Exactly, it's unavoidable as ozone is everywhere in the air. This is our tensile test. The maximum tensile force our belts can withstand before they tear is one of their most important properties and usually includes a large amount of spare capacity so that the belt drive can continue to transit maximum power even after 10 years of use. So the belts are always designed with a safety margin. Yes, a very large margin, so the belt can safely handle everything it has to go through during its lifetime. We're now going to see what force we reach before this belt tears. A belt normally has a tensile strength in excess of 35 kilonewtons or 3.5 metric tons. That means you could easily hoist a fully laden sprinter van with it. That sounds like a huge amount. It certainly is. Here we have our climate chamber, where we conduct cold impact and low temperature tests on complete engines, including customer engines. I see. There you have it. So you're able to save yourself trips to Finland because you have everything you need here on site to carry out tests as if you were there in the cold north? Exactly. This is where we carry out the low temperature tests for investigating noises from engines. We once had to test a customer engine that only suffered a noise problem if the car had been parked outside overnight at 0 degrees. Only then would it make a squealing sound for 3 seconds when it was started. That is extremely difficult to replicate. That's so specific. It is. That's the plan though. We bring the customer engine here and try to reproduce the exact noise. If we manage to consistently reproduce it, the colleagues in product development will start work on improving the belt and eliminating the noise. It looks as if things are about to get chilly. You're absolutely right. These are our low-temperature test rigs, where the belts are tested for resistance to the cold at -40 degrees. That's really cold. Imagine you're in a ski resort and leave your car outside overnight. When you start the engine in the morning, the belt will be frozen when it starts running around the pulley. It must still be elastic when it does this and not kink so that the compound doesn't start to crack. So the belts are started here more than 100 times at -40 degrees to check they run smoothly. I wish I could go on that many skiing holidays. It's pretty cold here. Let's go and warm up somewhere. It's about to get much warmer as the test rigs in our endurance testing section run around the clock, so they give off quite a bit of heat. We conduct tests on over 150 test rigs under all sorts of different conditions: cold, heat, mud, water. However, our work mainly focuses on continuous operation at high temperatures to check the belt's service life. I run 5 kilometers a day on my treadmill, but that's not quite the same, is it? That's right, we run a little further here. We aim to replicate a service life of 150,000 kilometers in 150 hours. What's important is that the belt emerges at the end with the same pattern of defects as after 150,000 kilometers of operation. So the belts are tested under overload conditions, as we would otherwise have to test them for years before getting any results. We test at higher forces and torques than the belts will actually be subject to. Sounds like I'll have to turn my treadmill up a few levels. Yes, if you want to be on par with our belts. I'm not sure I'll manage that. This is our hydropulse shock testing machine. In the middle here, we have a heat chamber at a temperature of 150 degrees and a timing belt that has been cut open. Every time there is an impulse from the fuel injection pump, the timing belt is deflected due to the pump's high load. This is reproduced 20 times a second here in this fatigue test. So it's a sort of time-lapse test. Exactly, we manage around 1.7 million impulses a day. But the belt will have to endure over 700 million during its lifetime. So we test under overload conditions with increased forces and then work out the belt lifetime at lower forces. Meaning the belts have a built-in safety margin again. Exactly. This is our test rig for measuring the coefficient of friction of multi-V belts. The belt is driven with a large wrap angle here and a small wrap angle at the second pulley. This is where the torque is increased until we have 100% belt slip. So this is all to do with friction and slip. Exactly. But you need a certain amount of friction and slip, don't you? That's right, we are faced with a bit of a dilemma in fact. On the one hand, we want the coefficient of friction to be as big as possible so that the belt can transmit high torques. On the other hand, we'd like the friction coefficient to be small so that the belt doesn't make any noise if it slips. So we have to aim for somewhere in the middle and maintain that throughout the belt's lifetime. Now you've seen how new belt technologies are checked before they are launched and arrive in your workshops. Tim and I hope you enjoyed watching. If you did, please give the video a like or post a comment. Until next time. See you.